In this lesson, we'll talk about acceleration analysis of 4-bar linkages. It's similar to velocity analysis and position analysis. I want to go a little bit into why acceleration analysis is important. It's important because we can use Newton's laws and inertial forces, F equals ma, to determine how much force and internal stresses are put on objects. And from this, we can determine how strong these objects need to be. So this is why it is important that we look at acceleration analysis. This should read acceleration analysis. So if we look at the acceleration analysis of link 2, of link 3, link 4, and link 1 is the second derivative of position. And again, it's the first derivative of velocity. So similar to motion and velocity analysis, we've got this nomenclature laid out. We've got our angles of each of our links laid out, the lengths of each of our links laid out, and then we've got the x component and the y component of the second derivative of the vector loop for position. So when we have the x component and the y component, we've got ourselves the tangential acceleration and then the radial acceleration. This is why you see two expressions here for the x component. So they're similar all the way down. We're going to take the derivative of velocity with respect to time, or the second derivative of position with respect to time. What we end up with is negative a, so the length of link 2, times the angular acceleration of link 2 times sine of theta 2 minus a, the rotational velocity of link 2 squared times cosine of theta 2. So that's for the x component. And for the y component, we have a alpha 2, the angular acceleration of link 2, cosine of theta 2 minus a times the angular velocity of link 2 squared times sine of theta 2. So in this 4-bar mechanism is a 1 DOF system. So we have to have one input. In most cases, it would be theta 2 is the input. In order to complete a velocity analysis, we need to have omega 2 as the input. And in order to complete the acceleration analysis, we need to have alpha 2 as the input. So with these inputs to the system, we can solve for position, velocity, and acceleration. Now it's important to note here we need to solve position first, we need to then solve velocity, and we need to solve acceleration. It's also important to note that these position, velocity, and acceleration build on each other. So what we have here is for every value of theta 2, okay, we're going to get new values of theta 3 and theta 4. So we have to solve this in this order, right? Given a theta 2, we can solve for omega 2 and alpha 2. When we change theta 2, we're going to get a new omega 2 and, a new omega 3 and omega 4, right? So these are known, these don't change, but we do have to solve this every time. So we take the components of our acceleration, x component again, and y component, and we can take our acceleration vector loop equation, which is a2 plus a3 minus a4 minus a1. Again, this expression works for the diagram that I presented previously. I have rearranged and collected these expressions into x components and y components. So again, here's what you'll see. This is from link 2, this is from link 3, this is from link 4, and this is from link 1. We know this about the system. We know that theta 1, omega 1, and alpha 1, we're going to say that these are 0 because the ground is not moving. when we say that there's 0, we can simplify this expression for x. So we end up zeroing out this value and zeroing out this value because alpha 1 and omega 1 are 0. Similarly, for the y components, we can zero out this last two values within this expression. From here, we've got our simplified x component and y component expressions. We can solve these two expressions simultaneously. And when we solve them simultaneously, we end up with these two expressions for alpha 3 and alpha 4. Okay? So what we have here is, this is going to be acceleration analysis. Okay? We've got expressions for omega 3 and omega 4. And we have two solutions for theta 3 and theta 4. Okay? These need to be solved first with the equations that I've given. These then need to be solved next, and finally you can solve these. These are the expressions that need to be substituted back up in here. I just simplified them for you. What you will notice here is the following are A, B, C, D, E, and F. We know all of our A's, our B's, our C's, and our D's. Our theta 3 and our theta 4 change. This is known. This is known. This is known. This is known, right? So the things that we don't know are omega 3, theta 3, omega 4, and theta 4. So again, we've got to solve this first, this second, and this third. So you can imagine calling functions within MATLAB and then passing these solutions to another MATLAB function, and then finally passing these solutions to another MATLAB function. And I'll discuss some examples on that. If you have any questions, please post them to the discussion board, and I will attempt to answer them.